Chiral. What do you got for chiral?
Mirror image, or it's a carbon that is its stereocentric.
Okay.
Alright.
It's a carbon or molecule with a stereocenter. Okay, and the stereocenter?
Geometric isomer.
It's not a geometric isomer.
Oh, okay.
Geometric isomer deals with what?
Oh,
Double bonds?
yes.
So what's your requirement for something to be considered a stereocenter?
4 different connections.
A carbon connected to 4 different things, right? I know this seems not very scientific when I say things, but why am I saying things and not atoms? Could a carbon be a stereocenter, be chiral, and be connected to 4 carbons? Yes. How?
If the carbons were connected to something else.
If each of those 4 carbons had something different on them. So let's say I'm a carbon in the middle and I have 4 carbons connected to me. This carbon has a fluorine, that one's got a chlorine, that one's got a bromine, and that one's got an iodine. Even though it is initially connected to 4, you're not allowed to just, here's my carbon, and then count those 4 things it's connected to. You have to continue on with the chain. 2 of those chains have to be utterly identical to not be chiral. If they are not utterly identical, then the molecule is chiral. So don't just stop at the first atom and say, oh, I see 4 carbons, or I see 2 carbons. I'm done, because those 2 carbons might not have the same things connected to them. And an enantiomer.
Here's the mirror images.
Yeah, it's the mirror image. So when a drug company goes to sell a drug and there's a stereocenter in the particular drug, what do they need to do?
Make sure that there's not opposite, just that it's not a left hand.
What'd you say?
Separate them?
They need to separate them, and then they need to do what with the 2 things that are separated?
Yeah. Where everything's located.
Find out which one works. 99 out of 100 times, one of them is going to do nothing or do bad things, and the other one is the therapy version. So if you have a drug that's got a stereocenter in it, you need to separate it out into its 2 components and then determine which one is the thing that you want. What if you've got a drug that's got 2 stereocenters in it? God forbid that. What does that mean? How many different molecules do you have? 4, 2 to the second. You have 4 different molecules. So you make this drug, you have 4 things that look very similar to each other, but they're actually not, because there are 2 mirror image sections in there. So that means you have 4 different possibilities. So you're gonna have to separate it into its 4 possible versions and then figure out which one is the version that's actually doing the therapeutic effect. So do you want a stereocenter in your drug? No, you don't want a stereocenter in your drug. What are the requirements for something to be chiral? Well, that's pretty much the same thing as we had right here, right? I need a stereocenter. I need 4 separate connections. This looks terrible. Draw 2 enantiomers. All right. Let's go with a carbon and a hydrogen and a methyl group and an amine and a carboxylic acid. And then I'll draw the carboxylic acid on this side this time. Does anybody know what these things are? What is that functional group? Nope, it's not nitro. Nitro is NO2. It's an amine. And what is this functional group? Acid. So this is it's an amino acid. Yep. All right, so what are we going to do? We're going to name some molecules. Okay. There's a couple ways to name these guys, but hopefully you name them all for what as the base name? Benzene made it easy on you. So the first one's benzene, and what's attached to it? I'm sorry, did you say 2-propyl? Why?
Because it's on the second little notch. Doesn't matter.
Really? It's on the second little notch?
Or the first, or the third, or the fourth.
It's on any notch you want it to be, so what notch is it? The first one.
Okay.
Are you okay with that?
I'm okay with that.
Just because.
I thought about that as I was writing them out. So.
Just because the orientation is, I mean, here's the molecule, right?
Mhm.
And you think that's number one because it's pointed up?
Yeah.
Okay, so now where's number one?
On the side still.
Anywhere you want it to be, right?
Yeah.
So it totally doesn't matter. I mean,
Okay.
is this a dry erase marker?
Yes.
Is this a dry erase marker? Okay. The next one, what do we have here? Isopropyl. Benzene.
Okay. We'll just ignore the twos all in the name.
Yeah. Next one? Butyl. 1, 2, 3, 4.
Yep.
Next one?
Mhm.
Sec-butyl.
Mhm.
Next one?
Trimethyl?
Nope.
Maybe? No, I knew I got. Something try.
Oh, I'm sorry. It's not.
What is it?
It's a T. And then the last one?
I did get it right. Sec. Okay.
Just drawn a little bit different, but doesn't matter because there's free rotation around single bonds, so those things can be wherever the heck they want. So what's the explanation for this line drawing?
Is it bipon for formation, or am I wrong?
Say again?
Bipon? Pipon? I don't know. I just read it in the thing here, right here. Right here.
What's a bipon?
It says right here. It says formation of a fully delocalized bipon. Pipon.
Pi.
Yeah.
Okay.
Pipon.
All right.
Sorry.
Yeah.
I knew what I was trying to say, but.
Okay.
I just
So
couldn't get it out.
this is a pi bond that's delocalized. Why? Where's the pi come from?
Yeah.
More specific. They're p orbital electrons. The electrons themselves come from p orbitals. So whenever I've got a p orbital electron making a bond with another p orbital electron, we call that a pi bond. And so it's got a pi bond. But the interesting thing about it is the pi bond doesn't say segregated between the carbon atoms, right? There isn't a double bond and a single bond and a double bond going around the structure. The structure actually is taking those electrons that are supposed to be between two carbon atoms and allowing them to rotate around all 6 carbon atoms, above it and below it. So it's 2 donut shapes. So this circle inside of this hexagon shape is trying to, it's showing you so the delocalization has to do with what? Where are covalent electrons supposed to be where are the electrons in a covalent bond normally found? In between 2 atoms, specifically between 2 atoms. And where are these electrons found? Are they localized between 2 atoms?
They're in the middle, aren't they?
They're not in the middle. They're over the top and over the bottom. So they're not set in a local position between 2 carbon atoms. Those 6 electrons are allowed to be able to travel all across the 6 atoms. So that makes this really stable. It makes it a giant covalent bond on the top and the bottom, which provides the molecule increased stability. Name this one. So what do we got here? 1, 2, 3, 4, 5. Okay. Did anybody ever come up with a different name besides pentylbenzene?
Yeah, the toluene pento.
No.
Okay.
Are we good with that? Those are your only 2 options for this molecule. Well, I mean, you could put 1 benzyl pentane, but benzyl and phenol, same thing. How come it's not toluene, Deb?
There's only,
Because there's 5 in a row, and toluene is 1 carbon attached to it. So here's a toluene right here, right? Yeesh, that was awful.
yeah.
That right there is a toluene. But if this got longer, that's not a toluene anymore.
Okay.
Okay, so there's lots of names for this one, right? I mean, 10.
Really?
So somebody want to give me 1? 3-ethyl toluene, like it. So what John said is, if I cover up this methyl group right here, what I'm seeing is a toluene. And then relative to that methyl group on that toluene, I move 1, 2, 3 carbons over, and there's a 2 carbon chain there, so that's an ethyl. What else could he have used? No, it's meta. Para is on opposite sides. So you could have put meta ethyl toluene or M ethyl toluene. Any other names you could have used? You could have used 1-ethyl 3-methyl benzene, or you could have said meta ethyl methyl benzene. Those names would have worked out as well. How about this next one here with the fluorine and the alcohol group? That's probably the easiest one. O-fluoral phenol. That's probably the first one in the list of names you would get if you were to go to try to purchase this. So if you're going to go to a company like Merck or Dow Chemical or Bayer or a bunch of other different chemical companies, they would have this molecule's picture there. They would have it listed, all the possible names for it, all the different aliases. And this one would probably be the first one. Somebody have another one they want to ask me about?
Isn't it ortho aniline fluorine?
No. Can't be, because aniline has a what on it? NH2
Yeah.
as an NH2 group. So the only common name of this one you could have used is phenol.
Okay.
You could have called it benzene, right?
Yeah.
You can always call it benzene and then just name the things attached to it. So this is a hydroxyl group attached and a fluoryl group attached. Fluoro F comes first, so that'd be 1. So you call it 1 fluoryl, 2 hydroxyl, benzene. That works. How about this last one? Para benzoic acid, sure. But para nitro benzoic acid. So the COOH on the benzene ring is definitely benzoic acid. And then I've got something attached to it, and it's a nitro group, and it's directly across from it, so it's para. Or it could be 4-nitro benzoic acid. Draw a structural diagram of a molecule containing primary, secondary, quaternary, and tertiary. All right, so C, 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 C. So now I got a quaternary in the middle. C, C, and I got a tertiary right there. And I got a secondary right there. So I'll just throw on my H's. So these yellow ones are all what? Those guys are all primary. And what's this guy that's green? Secondary. And this blue one? Tertiary. And then this red one? Orange one, whatever? Quaternary. Which one of those is the least reactive? Quaternary. What's the most reactive? And it's literally just based on accessibility. The one that's blocked off the most is that orange one in the middle, and the ones that are accessible are the ones on the outside, so the yellow ones. Phenol. Okay, so phenol is C6, H6, O. And O2. CO2 and H2O. That doesn't really matter. I'll just throw down gases for everybody. Let's make that a little more clear. 6. Okay, so I don't know. Can I just balance that out easy? If I put a 6 right there, and then if I put a 3 right here, and then 3, 12. 7? Is that it? So that's 12, 13, 14, 15, 14, 15. Oh, okay. So are you getting a pattern with these things? If you've got carbon and hydrogen or carbon, hydrogen, and oxygen, what's your product going to be if you burn it? It's going to be CO2 and water. Yeah. So when a forest fire burns, what's the product? CO2 and water. Primary component. Okay.